So what happens here is when you're looking at graphs or functions, when we get into those a little bit more, you're going to be asked to talk about the domain and the range. And what happens here is when you're looking at domain, instead of just saying what's the domain and range, they're asking you what are the x values, what are the y values. There are a little bit of rules here and there about them. Yes, sir?
Why can't they just say what's the x value and what's y value?
Because it's not as cool. Because it's math, exactly. We have to make things sound a little bit more complicated than they need to be, just because that's what they do.
We are where we are.
They want us.
Because now you sound cooler when you're talking about the domain of this function. Instead of just saying the x values.
Okay.
It sounds cooler.
Yeah, it does.
Chicks dig it.
Yeah. All right. Math is fun.
Making all that up. It's kind of like that great story of slope. You guys are so mad at me. I love it. The other part of that I want to look at is a function. In this class, we talk lots and lots and lots about function. And there are specific rules that garner why something is or is not a function. And it's quite simple to remember. When you're dealing with a function, that means that in an equation, for every x value, there is only one y value. So for every x value that goes input, you get one y value output. Yes, sir?
I just have to ask, because looking at your F, did you ace every true-false quiz you ever had?
That's good. No. But yeah, I see what you're saying. I never thought of that. I meant true. I meant false. That's a good question. No.
I forget who it was, but one of our teachers said that, yeah, his favor is requiring us to write the entire word out instead of kids doing that.
That's awesome. No shortcuts there, right? And another thing we were asking about why we use domain and range, the real definitions they use, the big words, a definition of a function is for every value in the domain, there exists exactly one value of a corresponding range. For every x, there's one y. That's why I use that.
Oh, so basically it's like you say x value, you're like a simpleton, like.
I don't mean like simpleton, but it makes it a little bit more user-friendly.
Yeah.
Because we're not collegiate math people. We're talking that
they're
crazy.
trying to wean out the incapable math here.
Yeah, exactly. So the other thing that we do with function stuff is that you guys have all, another way to look at, to tell whether or not something is a function is you look at it graphically. And the way that we do that is if on a regular old XY coordinate plane, if you've got a graph going through, in order for something to be a function, it passes what's called a vertical line test. So what happens here is that for any graph that you have, if you take a vertical line and you take the vertical line all the way through that graph, if it only touches the graph at one spot, it's a function. If it touches the graph at two spots, it's not a function. That means that that x value has two corresponding values of y, no longer a function. So that's something called a vertical line test. You will see that from time to time. You will see graphs like a parabola. And a parabola is a function because it touches at just one spot all the way through. A hyperbola, or when we get into stuff like this is not a function now. We will graph things like that. A parabola turned on side. Yes, sir?
How does it not touch it multiple spots?
Here?
It's on the other.
See how it's only touching the graph itself?
Yeah, but like the spot where.
Now remember, I'm not. This isn't.
Oh, you mean like two different spots at the same time?
Correct.
Oh, all right.
It only touches it at one spot. Yeah. So for every x value, there's only one y value that's going through.
I thought like at the same time.
No. If it touches at two spots at the same time, it's back. Not a function. Same thing when you look at circles. A circle will not be a function, because as you draw through this, you're going to touch the circle in more than one spot. So the equation for a function, or equation for a circle, is not a function. All right? And we go through this a little bit from time to time. A lot of the stuff that we get into, especially next week, one of the first sets of functions that we look at are going to be called piecewise functions. And I think that'll be Tuesday. And those kind of tend to have breaks in their continuity, but they still retain the functionality. Yes, sir?
So a horizontal line is a function,
Yes.
but undefined line isn't?
Correct. Correct. A horizontal line passes the vertical line test. A vertical line a vertical line will not pass it because it touches it and it becomes an infinite touch.
Yeah.
So no matter how many vertical lines you have, they're never going to be. All right. That's 2.1. Let's look at 2.3. Quick graphs. I know it's not the title of the section. I like to think that it is because it makes a little bit more sense. When we're looking at quick graphs, as you guys have all grown up and gone through the ranks of all the different math classes, more often than not, you guys have been taught to graph things in slope-intercept form. Solve the equation for y, plot your y-intercept, and walk your slope. And that's how you're able to graph lines. It's very simple, it's very methodical, it's the same thing over and over and over again. Nothing really changes. You use that y equals mx plus b. So if you had to start at a graph, and I'm not going to use any graph paper really today, I'm just going to kind of do some rough graphs for right now. If I had to do something where it was y equals 2x minus 3, where would I start that graph? On the x-axis or the y-axis? Which one is that? Okay. So I go down 1, 2, 3, and then I go up 2, right 1, up 2, right 1, and so on. And you guys have been doing that forever. That has not changed at all. The other method of graphing is one that you're going to find even easier. Do you guys remember what something's called standard form? What was it? You just remember the word?
I remember the name.
Standard form was that form that nobody liked. AX plus BY equals C. Vaguely remember that now?
Yeah.
Remember there were certain rules that applied to standard form? There were some rules that applied to standard form in order for this stuff to work. In standard form, you had to have A was positive. A and B are both not equal to 0. That means A could be 0, B could be 0, but both of them can't be 0. And I think the other real main one was that A, B, and C all had a GCF of 1. And that would be very simple to do if you had A was 2, B was 6, and C was 12. You just divide everything by 2 to simplify it out. So standard form was something like that. The reason that we taught you guys standard form back in the day of how you move stuff around is because it allowed you from standard form to move to the different forms by just solving for specific variables. The reason that you guys were solving for specific variables throughout the times from this is to get you in the habit of working with what are called literal equations. Those of you guys that go more and more into the sciences, you solve equations all the time for different parts of them. And that was one of the main reasons you did this. But the main reason that I like standard form now, you guys will too, is because of the following rule. If I have a graph, and I'm going to use a grid just for this example here. You don't have to have a grid on your own. But if I have a graph, and I have an x-intercept here, That's where it crosses the x-axis, right? What is the coordinate of the y value at an x-intercept? 0. Also, if I cross the y-axis, what's the value for x? 0. So at my x-intercept, my y value is 0. Do you agree? At my y-intercept, my x value is 0. So that means when I'm looking at standard form, well, let's even do it better this way. If I have the following equation written in standard form, 2x plus 3y equals 12, if my y-intercept is 0, I just cover it up, right? And it's gone. What's my x-intercept? 6. If I cover this up, what's my y-intercept? Here's my line. Done. Quick graphs. Cover and solve. Cover and solve. Works every time. We use this a ton. We use this a lot. It's so easy to graph anything once it's in standard form, because all you do is you cover up the x value, solve for y, there's your y-intercept. Cover the y up, solve for x, there's your x-intercept. It's a very nice trick way to do it. Connect the dots, and you're done. And if you want to get rambunctious, you can still figure out your slopes. You can walk it if you want. You have zeros and numbers. You don't need it. And that's all it is. Have you ever seen that? Good. Let's try another one. I just did this one, so do. Oh, I have this one here. Same idea. And I'm not going to use graph paper. I want us to do rough sketches because we don't need to see perfection here. We don't need perfection on graphs because we want to get just a quick visual representation of what something looks like. We use this a ton in chapter 3. In chapter 3, we do what are called constraint problems, otherwise known as linear programming. And not only will we I'll show you an example here in a second, but you'll be doing these quick graphs, but you're going to be shading them as inequalities as well. And by using this quick graphing method, it's very, very simple to do this. So once again, I have 3x minus 2y is 6. All of my rules work for standard form. A is positive. A and B are both not 0. B can be negative. There's no rule that says it can't be. All these guys have a GCF of 1. So when I go to just kind of make up my graph, what's my x-intercept? What's my y-intercept? Done. Yes, sir.
So you already have the equation there?
Yeah.
You just make it up.
Okay. Because now when we go into when we get into chapter 3, I'm going to change this equation to an inequality. I'm going to ask that you shade it because I'm going to put boundaries in here and I'll look for shaded areas because you can maximize or minimize profits and things like that with this style of graphing. And that's what we're heading towards eventually. So quick graphs are going to become your best friend. Pretty slick, isn't it? What's wrong? Are you mad at your prior math teachers now?
No,
Other classes were.
no.
I'm sorry. All right, back to the other one I had here. Once again, horizontal and vertical lines. Every single horizontal line always has the same start of the equation. Every horizontal line starts with what? Every horizontal line starts the same as the same equation. What does it start with?
Y equals.
Y equals. Good. Every horizontal line always starts with y equals some number. And then every vertical line always starts with y equals some number, x equals some number. One thing that will occur with some of these things, and this is why one of the reasons I don't like to do a lot of graph paper, your intercepts can be fractional, and that's fine. There's no rules that says you can't have fractions or decimals. But I don't like decimals. I don't. All right. My general rule is with decimals, if the problem starts with a decimal, you can give me a decimal. If it doesn't start with it, just keep it in fraction form. And the calculators will convert all decimals into fractions. I know that there will be a weird one every once in a while. It might not be able to, and if that happens, it happens. Kind of really all I got. I mean, can you graph that if I gave you that? I know you can't, but. So, there's really no reason for me to continue. Section, what is this, 2.3, which is on page something or another. May I steal your book? Can I figure out what numbers I assigned you the last hour? All I want you to do, it's section 2.3, which is page 87, 43 to 51. You just do those. It's 9 problems.